Hey everybody, welcome to the first lightning talk. My name is Mahmoud, and I'm going to present parts of my master's thesis, which I did at the Technical University Munich, and I completed a couple of months ago. So we've heard today a lot about neurorobotics and simulations and virtual environments. My thesis is also about that a little bit. It's actually based on this experiment by Floriano, which was conducted in 2001. They did a physical experiment in which they used a box where the walls were painted with black and white vertical stripes of random widths from a specific range. And they placed a small robot in this box of 2 wheels and equipped with a camera module. And interfaced to this robot was a spiking neural network of 18 sensory receptors and 10 neurons. And the idea was to learn or evolve a network that can move autonomously without colliding in this environment. So the sensory receptors transmit visual signals read from the camera and the errors between the actual and desired speeds of the wheels. And then these signals are fed in a feed-forward way to these 10 neurons, 4 of which control then the speeds of the wheels of the robot. So each wheel is assigned 2 neurons, one setting the amount of forward speed and the other setting the amount of backward speed. And the actual speed is then the algebraic sum of both. The way the network, the way the connections work in the network, and the way it is decided upon whether a neuron is inhibitory or excitatory, was encoded in a binary genetic string. So they generated a population of 60 genetic strings randomly, and they evolved over time using this fitness function here, which chooses the individuals that can move as faster and more forward as possible without hitting the walls. They tested each individual for 40 seconds in this environment, divided in 100 milliseconds chunks. At the beginning of the 100 milliseconds, the sensors read, so the camera and the encoders on the wheels, and then the network keeps spiking. And at the end of the 100 milliseconds, a new value for the next 100 milliseconds for the speeds of the wheels is set. So what I've done is I've built this environment virtually. I used Python, and I created this arena. You can see here the red dot is the robot, and the blue lines represent the visual field of the borders of the visual field of the robot. This angle was 36 degrees. All the specifics were mentioned in this paper. You can see here what the robot can see. So this is the wall between the blue lines here. And I also created the 60 individuals of this genetic string encoded here. So here you see the 10 neurons, and the black squares represent a connection from the 10 neurons to this neuron, or from the receptors to this neuron. And the blue or red dots here represent whether a neuron is excitatory or inhibitory. This started out random and then evolved over time. The specific neuronal model they used in this experiment was not available. I used NEST to simulate the neural network, by the way. And the neuronal model they used was not available in NEST, so I used 2 different neuronal models, the leaky integrate and fire model and the multi-adaptive threshold neuronal model. Compared the results of evolution over 30 generations, and the multi-adaptive threshold neural network neuronal model performed better. But at the end, it was successful, and the robot learned or evolved autonomous collision-free navigation in the environment. So there were some similarities I found between my test in the virtual environment and the experiment conducted in the real world, is that you can see here the firing rates of the 4 motor neurons over 40 seconds when individuals tested. And it was observed in the original experiment that 1 neuron does not fire at all. That means one of the wheels is constantly rotating forwards and the other wheel is controlling how the robot turns. This was also observed in the virtual environment. I've done other things I will happy to talk about to you later. I've tested reinforcement learning in this environment as well. And yeah, to conclude, please come talk to me later.